So good afternoon, everyone. I'm E, and I've been working on this project with my supervisors, Kate, our team, Matt and Reese, to optimize the real-time control rainwater harvesting systems. And this project is also one of the Optima industry projects in collaboration with Melbourne Water. So today I would like to take you through the journey, how we went from the simple optimization model for the very beginning to a more comprehensive one, and finally how we return to simplicity to enhance our rule-based control using the insight that we gain from optimization. So before talking about all those, I would like to first share the background of our project. So the motivation behind this project is to make our urban water system healthier. In recent decades, due to the rapid urbanization, we observe a significant increase in the amount of impervious surfaces, which are any surfaces covered with water-resistant material like pavement and rooftops. And this increase in impervious surfaces has led to an increase in surface runoff during rainfall, which exacerbates flooding and channel erosion. Meanwhile, it also reduces baseflow, which decreases water quality and wetter habitat for aquatic species, and also poses threats to ecological integrity. And in our project region, the foraging habitat for platypus has been degraded, which threatens the local platypus population. So we want to help restore the natural foraging to support their long-term survival. And it turns out that the real-time control rainwater storages could be one of the solutions to improve the streamflow conditions. So the rainwater storages intercept the rainfall, which reduces the stormwater runoff. And the real-time control valve also allows the tank to actively release rainwater more naturally back to the stream to restore baseflow. And at the same time, they also provide an alternative water source for household use. And we observed in a previous study that the collaborative operation of multiple storages can achieve better system performance. And we want to build on that idea, but expand it to a much larger network of distributed small and large rainwater storages. And we use optimization to control the systems based on the weather forecast. And we hope that this project can provide a template for water management and ultimately to provide to help deliver smart cities and towns. And we are developing and testing our strategy for controlling the systems through an experimental study in Mongo Creek in Melbourne, which also provides critical habitat for platypus. And there will be over 100 tanks of like small and large rainwater tanks being installed over the catchments. And we also have 3 larger storages, which are the lakes and ponds, and 3 monitoring points, which are denoted by this red dot here and there, to represent the critical habitat for platypus along the creek. And all the tanks, lakes, and ponds are real-time controlled. So basically, we want to control the releases from the storages to reduce flooding, improve water supply, and also restore baseflow. And there are, in fact, many aspects to consider, including how to formulate the objective to better reflect our goal, how we model the water routing and flow dynamics, etc. But just like many other projects, we started with a very simple model. So this simple model has 11 conceptual tanks. So we scale up the capacity of each tank so that they represent all the tank in its subcatchments. And we also include the 3 large storages, as mentioned before, the Belgrave Lake and Baseflow Ponds 1 and 2. And in this model, we optimize the daily releases from the storages, and assuming that the releases from the upstream storage can reach the downstream monitoring points within a day. And this problem is formulated as a multi-objective based integer linear programming problem. And we combine the objective using the weighted sum method with the weights determined by the analytic hierarchy process. And we use model predicted control, which basically means that we optimize the release plan for the next 7 days based on rainfall and streamfall forecast. But only implements the release plan for the first day. And then on the next day, the position horizon shift forward, and we redo the optimization with the updated forecast. So in this way, the future events are considered in decision making, and the impact of focus error can also be reduced. And we got the 7 days rainfall from the bureau and generates the 7 days rainfall forecast using a neural network based on the bureau rainfall forecast and also past rainfall and streamfall records. And in this model, we have 4 objectives. The first objective is fast reduction, which is formulated as minimizing the overflow from the tanks. And the second objective, water supply augmentation, is formulated as minimizing the water deficits for household supply. And the third objective measures the effectiveness of baseflow restoration using a piecewise linear function, which basically measures the scale deviation of the streamfall from the target flow interval. And the fourth objective is the equilibrium objective, which is trying to push the water level in the ending balance of the water level in the storages to half of its capacity. And it's designed to softly restrict the releases so that we have a buffer against focus error. And then we apply a mixed integer linear programming solver to solve the problem and determine the daily releases from the storages. And here is the computational results for our simple model, model 1.0. So we compare our MIP-based strategy, mixed integer linear programming-based strategy, with existing conventional and rule-based strategy, and also an NSJ2-based strategy. So the NSJ2-based strategy basically solves the same multi-objective optimization problem without combining the objective using an NSJ2 algorithm, which is a population-based meta heuristic that can solve the multi-objective optimization problem. And as we can see from the table, our MIP-based strategy managed to outperform the others in overflow reduction and baseflow restoration, with over 90% of the household demand being satisfied. And this average weighted distance to target basically measures the overall performance across the objectives. And we can see that our MIP-based strategy performed the best, and it also managed to outperform the NSJ2-based strategy with a much lower computational cost. And when we plot the storages level of different strategy and the rainfall over the year, we can see that our MIP-based strategy, as denoted by the blue line here, managed to release much more water from the large storages before heavy or continuous rainfall to create enough room in the storages before the storm hits to reduce overflow and also high streamfall.
Do you want to clarify conventional means?
No release. Yeah. And
do nothing.
Yeah, do nothing. And also our MIP-based strategy managed to release more water during the dry period when there's little rainfall and the streamfall is below the target flow interval. So that's pretty good results. That shows that we have made some progress. So we move on to analyze the impact of focus errors on our strategy. As we are doing optimization based on streamfall and rainfall forecasts, we are interested in seeing how the focus accuracy affects the system performance and whether our strategy could be further improved to handle the focus errors more effectively. So we compare the strategy with perfect and imperfect forecasts over normal, dry, and wet years. And for the average weighted distance to target, which is the overall performance measure, we can see that the difference in performance were much larger for wetter years. And this basically suggests that the focus accuracy was more crucial for wet weather, as there will be greater opportunities for improvement in all three objectives when there was a large amount of rainwater available. And we can also see the supply augmentation performance. So the supply satisfaction rate was largely affected by the focus area during normal and wet years, suggesting that there are substantial rooms for improvement in our current strategies, especially for the wet weather supply. And as the impact of focus area could fluctuate across different scenarios, we also test the strategy on 1,000 different 7-day periods with and without focus area. And we plot the difference in performance versus the magnitude of rainfall focus area in this plot and versus the full focus area in that plot. And the lower half of the plot, so the negative differences, basically indicates the scenarios when the focus area undermines the system performance. And for both this rainfall focus and full focus, we can see that the larger the focus area, the more likely the strategy was to be affected. However, as we can see from the green dots here and there, large focus area does not necessarily lead to huge impact on the systems. And here is a scenarios when large focus areas lead to small impact. So this graph here basically plots the actual rainfall versus the predicted rainfall. So the blue line here is the actual rainfall and the predicted rainfall is in orange. And similar for this graph here, we have the actual streamfall versus the predicted streamfall. And for the one here, so this plot basically shows the objective values for optimization with perfect focus in blue and imperfect focus in orange. And for this three measures, the overflow, supply deficits, and baseflow deviation, the lower the value, the better the performance. And we can see from this graph here, we have a large rainfall on day 6. It's like 45 millimeter. And the focus managed to predict that there is rainfall on day 6, but it largely underestimates its magnitude. And this underestimation also led to an underestimation in the streamfall forecast. However, when we look at the objective, the performance of the strategy, we can see that the optimization with perfect and imperfect forecast actually perform quite similar. And this is because the rainfall here is so large that it exceeds the system capacity. And the overflow and baseflow deviation can hardly be reduced even with perfect focus. And also because we apply the model predicted control and update the focus every day, if a large focus area get corrected in time, its impact to the systems can also be limited, which is also likely to be the case here. And in contrast, a relatively small focus area can lead to a large impact on the system as well. We can see for the scenario here, the focus area in the rainfall forecast and streamfall forecast were both much smaller in magnitude compared to the one above. However, the difference in the performance is much larger. And this is because the overflow and baseflow deviation could have been reduced with perfect focus. So as shown here and also the long-term test before, whether the system can handle the weather conditions can largely affect the impact of focus area. And the timely correction of focus area can limit its impact to the system as well. In addition, as we are generating the streamfall forecast based on the rainfall forecast, we often observe that they share similar patterns of overestimation and underestimation. And observing that a relatively small focus area can lead to a large impact on the systems, it seems possible to further improve our optimization-based strategies by incorporating uncertainties into decision-making. So that's what we did next. We took a step further and developed a scenario-based stochastic model to better account for the uncertainties in the forecast. And we try to optimize the expected objective function values on the different rainfall and streamfall scenarios. And we generate the set of rainfall and streamfall scenarios based on the predicted percentiles of rainfall depths provided by the Bureau. So basically each day we got from Bureau the expected rainfall, which is denoted by the solid red line, and also 25%, 50%, 75%, and 90% percentiles for each of the 7 days. And this percentiles and expected value basically comes from the example forecast from Bureau. However, we don't have access to all those examples. So for each day, we interpolate these values to approximate the rainfall distribution for the day, and we generate 100 samples for them. And basically we repeat it for each of the 7 days and join the samples independently across the time depth to obtain a set of 7 days rainfall samples. And we are aware that when we generate the rainfall samples this way, so basically independently drawn from each day's distribution, we lost the temporal correlations in the rainfall. And we have tried different ways to restore this temporal correlation, for example, like shock shuffling and Markov chain. However, it turns out that assuming independence is the most effective option. So we decided to keep it this way. But we may achieve a better result if the calibrated example from Bureau were available, as they will naturally incorporate the temporal correlation and also be consistent with the marginal information. And when I say marginal information, I refer to the percentiles and also the expected rainfall for each day. So we now have like 100 different 7-day rainfall samples, and we apply a density-based clustering method to group the similar samples and obtain a set of different 7 days rainfall scenarios. And the probability of each scenario here depends on the number of samples in its cluster. And once we get this, we generate the 7-day full forecast for each rainfall scenarios, so that we get a set of representative rain and streamfall scenarios. And we perform the stochastic optimization to determine the optimal releases from the storages. And here is our computational results for our stochastic model. So we can see from the table here, our stochastic optimization managed to perform better than the deterministic optimization with imperfect forecast orally. And also it performs better in the supply satisfaction rates. And when we test the strategy on different 7-day periods, we can see that the stochastic optimization managed to significantly reduce the number of scenarios that are largely affected by focus error. And for the example we mentioned before, when a small focus error led to a large impact on the systems, we can see that our proposed strategy managed to generate the rainfall and streamfall scenarios that better capture the actual realization of the rainfall and streamfall. And so it achieved a much better performance in the baseflow deviation. And its performance actually quite close to the deterministic optimization with perfect forecast. So that's pretty good and great. Building on the progress so far, we move into the next stage of the project. So we are aware that the fault protection and baseflow restoration are not only about reducing overflow and releasing enough water to meet the minimum flow requirements. To better support the stream ecosystems, the flow stability and peak flow also matters. So we decided to develop a second stage spatial temporal model to optimize for the flow stability, considering the flow dynamics within the systems. And this second stage model can be integrated with our previous model, either the deterministic or stochastic one, to achieve multiple objectives over different planning horizons. So basically, we took the optimal volume to release from the previous stage model to assess the flow stability over a day with a 6-minute time step to optimize the time and location of releases throughout the day. And instead of the simple model, we are now working with this more detailed model that accounts for the flow dynamics within the system. So we went out to measure the data for all the main streams and construct this routing model to simulate the water flow in the systems. So we use Monet's equation to simulate the water flow in the pipes that connect the tanks to the stream, and use Moskino quantum method to simulate the water flow in the stream channels. And as we can see from this hydrograph, the releases from the tanks and the flow from the other tributary and also flow from the upstream catchments can all contribute to the downstream hydrograph. And as the water continues to go downstream, it may enter lakes, and the flow rates at the downstream monitoring point is estimated by considering all these factors. And then we try to minimize the variance of the flow at the monitoring point, which is measured in 6-minute time step, by controlling the hourly release rates from all the storages. And we then assess the effectiveness of our second stage model by comparing its performance with a uniform release strategy. And we can see that our optimization-based strategy managed to achieve a much higher people reduction rates in the rainfall events, and it also achieved a more stable flow regime. And here we test our strategy on different typical scenarios, and we can see our optimization-based strategy as denoted by the blue line here and there. With perfect forecast, it can achieve a much more stable flow regime than the uniform release strategy. And when we use a more realistic forecast generated by the neural network, the performance is denoted by the gray dots line here. And we can see for all the scenarios, although its performance is affected by focus error, it still managed to consistently outperform or at least matches the uniform release strategy. And this result demonstrates the effectiveness of our strategy in managing water releases to enhance the flow stability and reduce peak flow. And in our case, we focus on keeping the flow stable, but we can easily tweak the objective function to meet other flow regime requirements as well. And up to this point, we have been focusing on the optimization-based strategy. And we have shown that it significantly mitigates flooding, improve baseflow, and also outperform the rule-based strategies. However, the optimization-based strategy can still be challenging to put in use in practice, considering the integration challenges and potentially high implementation costs. And on the other hand, the rule-based strategies may be preferable in practice, considering considering the practical concerns, as the rule-based strategy will be easier to implement, adjust, and also easier to communicate to the stakeholders. And given the outstanding performance of our optimization-based strategies, we know that there are still room for improvement in the current rule-based strategies. So we want to improve the current rule-based strategy with the insights we got from optimization. And we hope that the advanced rule-based strategy can serve as an alternative approach that offers greater flexibility and cost effectiveness than the optimization-based strategy. So to do so, let's first take a look at current rules. So in the current rules, we first perform the pre-storm releases from the tanks. So this is basically trying to create more room in the storages available before the storm hits so that we can reduce the overflow from the tanks when the rain comes. And the amount of pre-storm release from tanks is determined following the streamflow preservation strategy proposed in Shi's paper. I think she is online as well. Basically, we estimate the overall amount for the storages for the next 7 days to determine the total discharge volume from the tanks. And then we compare the release plan in these two graphs to choose the one with a lower discharge rate. So in the first plan here, we distribute each predicted overflow amount uniformly across the days leading up to its occurrence. And in the second plan here, we distribute each predicted overflow amount over the intervals between the last and current overflow events. And in this example here, we can see that the second plans achieve a lower discharge rate. So we'll just follow this trend here to do the pre-storm release. But like if the second overflow event here is much larger in magnitude, then the discharge rate of this plan may be higher than the discharge rate in the first plan. And in that case, we'll follow the first plan to perform the pre-storm release. And then we calculate the releases from the large storages, which is basically the amount required to achieve the minimum flow requirement. And we also allow the tanks to release more water to refill the downstream lakes or ponds when the tanks are more than half full. And then once we have the optimal release volume for the day, we uniformly distribute the releases over the day to determine the hourly release rates from the storages. And when we compare our current rule-based strategy with the optimization-based strategies, we can see that the rule-based strategy perform much worse in flood protection and baseflow restoration. And we can see from the graph here, so this is the tank behavior over the year, and this is the large storages behavior over the year. We can see that it released much less water from the large storages to control the flow compared to the optimization-based strategy. And also, although we're trying to reserve water in the tanks for household use, the pre-storm release from the tanks is performed regardless of the current tanks level. So this also limits our ability to improve the supply satisfaction rate. So we suggest that to improve the rules, we should use the large storages more effectively to avoid high streamfall events. And we should also restrict the water releases from the tanks to improve the supply performance. And instead of doing uniform release throughout the days, we may try to further reduce the peak flow by distribute more releases a few hours before the rainfall to reduce the peak flow. And just like what we did in optimization, we could also take into account the seasonal priority in the objectives when designing the routes. So with all this in mind, we propose this new rules. So the pre-storm release from the tanks is now determined by this longest discharge strategy, which we mentioned earlier. So uniformly distributes the predicted overflow amounts across the day leading up to its occurrence, because we found that this strategy is actually performed better in overflow reduction in the presence of focus error. And we also restrict the pre-storm release amounts so that they don't reduce the reserve volume in the tanks. And the reserve volume in the tanks is set seasonally. So for wet season, we set the reserve volume in the tanks to be the predicted demand for the next 7 days. And in dry season, sorry, it's the other way around. So in dry season, we set the reserve volume to be the predicted demand for the next 7 days. And in wet season, we lower the reserve volume to be the predicted demand for the next 3 days. And then for the large storages, we calculated the upper and lower deviation of the flow for narrower target flow intervals for the next 7 days. So this is trying to make our what we did in optimization when we're trying to push the stream flow close to the center of the target flow interval. And then we, just like what we did for the tanks, we perform this pre-storm releases so that we create enough room in the large storages to mitigate high streamfall events during the rainfall. And we also make sure that the large storages release enough water to meet the minimum flow requirements. And the reserve volume for the large storages are set to be 30% of their capacity to leave some buffers against unexpected flow variations. And we also restrict the large storages from releasing when the streamfall at the downstream monitoring points is already very high. And this is trying to avoid creating high streamfall ourselves. And for the hourly releases, we use the uniform release strategy as our baseline strategy, as it's actually observed to perform pretty well under normal conditions. But when a large rainfall comes, we set the hourly release rate to be reversely proportional to the forecast rainfall. And we also try to release more water from the storages before the rainfall events. And considering the travel time of the water in the systems, we try to release more water 2 hours before the rainfall events. And we now compare the performance of the old rule-based, the advanced rule-based, and also the optimization-based strategies using the same evaluation matrix as before. And we can see that the performance of the advanced rule-based strategy actually dominates the performance of the old rule-based. So it managed to achieve a much higher supply satisfaction rate without harming the other objectives. And as we can see from the graph here, so that the larger storages are more engaged in this advanced rule-based strategy as shown in the dots line here. And its performance is quite similar to the optimization-based strategy during the dry period when there was little rainfall and the streamfall is below the target flow interval. So this basically suggests that the large storages are actively release water to satisfy the baseflow target. So to conclude our work, we started with a multi-objective mixed integer linear programming model to optimize the daily releases for the rainwater harvesting systems. And then we incorporate the probability forecast to improve the performance under uncertainties. And we also developed a special temporal model to refine the scheduling for more stable flow regime and also reduce the peak flow. And finally, we improved the rule-based control using the insight we gained for optimization, and we managed to provide a more flexible options to the stakeholder compared to the optimization-based strategy. So that's basically what I did for my PhD. And for the future research, we may need to improve our stream flow models, which includes the rainfall runoff models and also flow forecasting models, and maybe also some calibration works to ensure that they are working well in practice. And we could also build a more comprehensive stochastic model that accounts for the uncertainties in rainfall, streamfall, and household demand. So as we mentioned before, we didn't consider the temporal correlation in the rainfall when we construct our current stochastic model. And we could improve that by building our own calibration models for the ensemble forecast. And also we didn't consider the uncertainties in the streamfall forecast model and the household demand. And we may take those into account in the future. And there is also a potential to explore optimization for an economic perspective as well, like working out the optimal rebate schemes to encourage better participation and also more efficient use of the systems. And it's also worth mentioning that the Melbourne Water has built a control platform with a user portal, which basically enables the tank owners to participate in the system operations. And our advanced rule-based strategy will be integrated into the systems to operate the network. And this also opens up new opportunities for further testing and improvement of our strategy. So basically that's it. And here's a lot of references and also some paperwork that we did this year.